Chapter 2, we're going to work with logic. And in Chapter 2, we're going to be doing some things that you might have seen in another course. Sometimes you'll see reasoning and logic taught in philosophy courses or in critical thinking courses, or potentially it has been taught in the past in our math, what do we call it, contemporary math course. Okay, so there are some little overlaps in this section with some other courses on campus, and so we'll see if you've recognized it from before. First thing we're going to talk about is a statement. A statement is simply a sentence that's either true or false. All right, so let's do an example of a statement. For example, the statement or the sentence, I ate eggs for breakfast. I either did or I didn't. This is either a truthful statement or a false statement. There is no gray area in between. Okay? This is a statement. Let's do a non-example. A non-example would be, I'll give you two non-examples for fun. What did, man, my stylus is not cooperating today. What did I eat for breakfast? This isn't a statement. Why not? It's a question. And the real sort of definitional reason of why it's not a statement is that there's no way you can say true or false. That is not an appropriate categorization for this sentence, right? It isn't. Here's another one, non-example. Eat your breakfast. What do we call that? A command. That's right. Again, it's neither true nor false. It doesn't fit the description of a statement, so it's not a statement. Now, the negation is the logical opposite of a statement, and it is written with a tilde. So if the statement has the name P, then its logical opposite, its negation, is a tilde P. Okay, like tilde on your computer keyboard. Kind of looks like a minus sign in front, but with some flair. Now, sometimes negations are very easy. For example, if the statement is the one that I originally gave you, I ate eggs for breakfast, what would be the negation of that? I did not eat eggs for breakfast. That simple, right? Very simple one. So let's finish the one that we just did, and we'll give that as an example. So the example for this one is if our statement is the one above, I won't write it down again, then our negation is simply I did not. Unfortunately, just simply putting the word not into things does not always work. And it does not always work once we introduce the next topic, which are called quantifiers. There are two types of quantifiers, universal and existential. Universal quantifiers refer to each and every element in the set. So you'll have words like all, every, no, or none. Existential quantifiers refer to one or more elements in the set. Some, at least one, there exists, are phrases you'll see when existential quantifiers are present. And this is where things get tricky. Now, the first set Universal quantifiers are the ones that get you in trouble. You never take out the trash. You always take my phone away. You ever get in trouble with those statements with your parents? You know, my kids don't like those statements, and I don't like it when they say them either, right? You always get mad at me. You always give my sister more whatever than you give me. They're the ones that get us into trouble. And the reason they get us into trouble is because they're so easy to be false. Because all it takes to make them false is one example where the parent or the child did not do whatever the parent or the child counterpart said they did, right? All it takes is one case for them to be false. So that's where the negations come in, is that one case to make them false. So let me show you an example of each one of these, and then we'll talk about what happens with negations for this. So let me do an example for a universal quantifier is something like all boys love their mama. That's a nice one, right? Nobody's going to get in trouble for saying that, so we'll go with that one. An existential quantifier, or example with an existential quantifier, would be something like this. Some people like swimming. Now, since we're here, I'm going to go ahead and create the negations for you for these, and then we'll talk more about how we create them in general. So the negation for this, all I have to do to negate something that says all boys do something is I need exactly one boy that doesn't do this, right? One boy that doesn't fit in this description. So we can say at least one. We could say there exists, or we can say some. At least one boy. At least one boy what? Does not love their mama, right? That's all it takes. One boy to make that statement false. Now, existential quantifiers. I need this some people like swimming, not to become some people don't like swimming. Because both of those statements can be true at the same time, right? I have to create a statement that cannot be true at the same time as some people like swimming. Any ideas of what I might do? Well, we know it can't be some, right? Yeah. There you go. We need a universal quantifier. Either, we've got a couple options, all or none, or no. I'll put the word no. We either need to negate this with the word all or no. We will create a universal quantifier for it. There's two ways we can write this. Both of them are technically correct. One sounds more like traditional English and the other one sounds a little bit more funny, okay? I don't think more funny is right. Funnier? Is funnier a word? I can never remember. Okay. Okay, so let me do all first. So if we have some people like swimming, what would we say that's the opposite of that with the word all? Right. So all people dislike or don't like, or some variation of that, don't like swimming. And that's technically correct, but it sounds a little bit funny. This one actually sounds clearer when we use the word no in the front. What would it have to say if we use the word no in the front? No people like swimming, or if you don't like no people, you can put nobody or no one, okay? But no people. Like swimming. Right? No one. The logical opposite of some people like swimming is no one does. Right? Both of those things cannot be true at the same time, and that's what a negation is. So let's take a look at doing some other examples of creating negations. Now, we established something pretty cool. Ellen's the one who actually said it, which was fantastic. The way that we negate with quantifiers is we use the other type of quantifier. So if you've got a universal quantifier, an all, an every, a none, you need to negate it with a some, or there exists, or something like that, okay? There at least one. If you have a some, there exists at least one, you've got to negate it with a strong universal quantifier. All, none, one of those. Every, depending on the language that's being used. So, here's our first one. All dogs go to heaven. And a lot like my example with all boys love their mama. So what would the negation be for all dogs go to heaven?
Some dogs do not go to heaven.
That'll work. Some dogs do not go to heaven. Now, a couple of comments. This isn't the only thing you could write. You could say at least one dog does not go to heaven, or there exists a dog that does not go to heaven. Those would be okay answers as well. Totally fine. It would not be correct logically. I don't mean spiritually, but I mean logically, to change any of the rest of the phrasing. For example, we would not say, some dogs go to hell, right? It doesn't work. We got to keep the logical structure of whatever's there. Don't change anything that's there. You can add words not, you can take away the word not, but you can't change the rest of the statement, okay? Everybody cool with that? So no changing the rest of the statement. And the next one's an example where sometimes people want to change the statement. This says, some of my classes this semester are hard. So what type of quantifier do I have? Universal or existential? I have existential, and the word is some, right? So when I'm creating a negation of an existential quantifier, it needs to turn into a universal quantifier. And so I need either the words all, every, none, no, something like that. So let's pick one. What would you like to say? None. Okay. I'll also do the one with the word all in a minute, just so you can see what that would say. None. If I used the word none, what would be next in order to create the negation, the opposite of this statement? What's next? What do I write next? Yeah, it looks actually this exact same, right? Some turned into none, so it's none of my classes this semester are hard. It's kind of like saying, if I said, some of my classes this semester are hard, and somebody else said, you're lying. Okay, well, if you were lying, what would the truth be? Well, the truth would be that none of them were actually hard, right? That's what would have to be the truth if that were a lie, if it were a false statement. Let's actually write down what it looks like if we put the word all in. So if we put the word all in, we would have all of my classes, and that's okay. But what would we have to do next? Ah, see, there's the point where somebody changed it, right? So what would we say instead? Are not hard. And I know it feels like saying are not hard means are easy, but that's actually not true. Have you ever had a class that's neither hard nor easy? I have. It's manageable. Maybe it's a lot of work. I've got other descriptors for it, but I really wouldn't call it hard or easy. So we want to be careful not to change what we've got. We're just going to say they are not hard. Okay? And that would be a logical equivalent to the one we already wrote. Either of those are negations, and they're both totally appropriate. All right. In deciding and showing whether statements are true or false, truth tables are often quite helpful. A truth table is used to show all possible true-false patterns for statements. So in a truth table, you have columns and rows. We're going to create a very simple truth table right here. In our truth table, we're going to have the statement P. And one possibility is the statement P is true. The other possibility is the statement P is false. And those are the only choices, right? It's either true or false. Statements have that property. They're one or the other. The second option then that we're told that we're creating for this is the negation. The negation is supposed to be the logical opposite of the statement. So if the statement is true, then the negation is false. And if the statement is false, its negation is true. And this would be our simplest truth table. Trues and falses for the statement and its negation. Once you have more than one statement involved, things become a little bit more challenging. You have more options, basically. A compound statement is two statements joined with the connective such as and, or if then. So if you have two statements and you put the word and between them, it becomes a compound statement, kind of like a compound sentence, right? But you had to start out with two statements. And it doesn't just have to be the word and. You could put the word or between them, or you could put the if at the beginning and then in the middle. You know, if it would just warm up, then I would go out and run. Right? That's an if-then statement. It would be a compound statement. So we're going to do three types of compound statements. The first one we're going to do is called a conjunction. A conjunction is an and statement. And it will be true only if both statements are true. On the way that you write an and statement, okay, so the both statements that I'm going to talk about are statements P and Q. Those are my two statements. The way that I write an and statement is I write P, I do an upside down V, and Q. Okay, that upside down V, you can kind of think of it as looking like half of an N or something like that if you prefer. It means and. The first thing I'm going to do is I want to draw out a truth table for the options, the possibilities of what could happen. So I have two statements. One statement is P and one statement is Q. One possibility is that statement P could be true and statement Q could be true. Yeah, they could both be true. The second possibility is that statement P could be true, but the second statement could be false. Our third possibility is that the first statement could be false and the second statement could be true. And what am I missing? They could both be false. Now, truly, it doesn't matter what order I put these statements in my table. But for the purposes of me being able to grade without just like pulling out my hair, it would really help me if you put them in this order. And it will help you too, because the back of the book when you check things is going to always be in this order. They're always going to do true, true, false, false in the first column, and true, false in the second one. Okay? It's a pattern. It's always going to be established that way. So when we're doing these together, I'm going to always model that. And if you would do that for me too, I would appreciate it. Now, so far, this has nothing to do with the and between them. All it is two statements and whether or not each of them individually are true. So let's take a third column in our truth table. And this column is going to be the column titled P and Q. And in order to justify with you and for you that this actually makes sense, we're going to give statements P and statement Q a sentence that goes with them. We're going to actually create a statement. So the statement that I'm going to create is P is the statement that I teach math. And Q is the statement I am a mom. Okay? And what we're going to do is we're going to consider cases of people that you hopefully will know across campus and see whether or not this would actually work. So I have people, and I don't, but pretend, they're all standing in the hallway. Okay? I've got 3 people standing in the hallway. And the first person walks in, and the first person is me. So I guess I have 3 people in the hallway besides me, I should say it that way. I walk in and I say, I teach math and I am a mom. And from what you know about me and the things that I've told you before, you would say, that's true. Because you know that I both teach math, because I'm your teacher, and you know that I'm a mom because I've shown you pictures of my children, right? So this is a true statement. And you'd say, she's telling me the truth. Because both statements are individually true. Next, we're going to pick on someone that I think many of you know. Who knows Dr. Auk? No, not very many of you know him. Well, I said it's a him already, right? Him. That's our key. Dr. Auk walks in. So for those of you who don't know, Dr. Auk is a man. Okay, Dr. Auk walks in and Dr. Auk says, I teach math and I am a mom. And you might giggle at him, right? Now he does teach math. He teaches contemporary math. Some of you probably had him for that. He teaches other classes as well, but he does teach math. But he is not a mom. And so when he walks in and he says, I teach math and I'm a mom, you would say, that's false, right? He doesn't do both of those things, so he can't put the word and between them. That would be a false statement. Okay, I'm trying to think of people over in the education department now that you guys know. How about Miss Young? Do you guys know Miss Young? Okay, it's Dr. Young now. Sorry, that's right. She did finish that, so she's Dr. Young. Dr. Young walks in, and Dr. Young says, I teach math and I'm a mom. And you would say, that's false. Why? She doesn't teach math. She teaches education courses, correct? Yeah, so that doesn't work. That would be a false statement if she walked in and she said, I teach math, I'm a mom, and I'm a mom. My last example is always the same. It's Dr. Whitlock. Dr. Whitlock comes in, and Dr. Whitlock says, I teach math, and I'm a mom. And you would say, that's false, right? He does not teach math. He is not a mom. That would be a false statement. In order for a conjunction, an and statement, to be true, both of the individual statements must be true. Otherwise, it's a false statement. All right. After conjunction, we talk about disjunction. A disjunction is an or statement. Okay, we're still going to use P and Q. For some reason, they're our favorite ones to use when we talk about logic. And an or statement is actually written as a V. Depending on how you write your V's, maybe it looks almost like an R for or. I don't know. You can pretend. But it looks like a V. We have the same setup that we had before. P and Q. We have true, true, false, false, true, false, true, false. And we have our column for the or statement, P or Q. And we're going to use the same P statement and Q statement that we had on the previous problem, okay, or the previous example. I walk in and I say, I teach math or I'm a mom. Is that a true statement? It is. It sounds a little bit funny to use the word or between since both statements are true, but it is true. Okay, we're using the word or to mean either or both. And both of those statements are true, so it is a true statement for me to walk in and say I teach math or I'm a mom. Dr. Auk was second. Dr. Auk walks in and he says, I teach math or I'm a mom. And you would say, that is a true statement because he does in fact teach math. Dr. Young walks in and Dr. Young says, I teach math or I'm a mom. That is a true statement. For those of you who were unsure, she actually is a mom. She has 3 kids, I think. That's right. But then Dr. Whitlock walks in and he says, I teach math or I'm a mom. Still false because he is neither one. So that was a false statement. So the only time that a disjunction is actually false is if both components are false. There's a lot of true going on in this particular truth table, right? Yeah. Okay, I think we have an example now of how to write a more complicated type of truth table. Yes. Okay. So anytime you're given a statement, conjunction or whatever's going on, you need all the components in your truth table. So your truth table will always start out with P, Q. No matter if there's a tilde Q on there eventually, it will start out with PQ, always. After that, you're going to look and see what else do I need from here. Well, I already have the P. I'm going to need the and part in a minute. But before I can do the and part, I need a tilde Q. So I need a column for that. So I'm going to need a column for tilde Q. And now I have each of the individual components because I have P, I have tilde Q. So now I can put it all together as a final column in my truth table, P and tilde Q. No matter what happens next, you should be able to set that part up because you're just putting all the components into columns. The other part you should always be able to set up is the first two columns because they're always the same. They're always true, true, false, false, true, false, true, false. Okay? So every component of that thus far you should be able to set up for every problem. After that's when we have to do the logic part of it. Okay? The logic part. Tilde Q. Negation. Negation of Q means I take the Q column and I do what? I reverse it. If it's true, I write false. If it's false, I write true. So my Q column right now says true, false, true, false. So what will my tilde Q column say? False, true, false, true. Okay. The next thing I'm going to do is I'm going to look at the columns that actually match up with the final statement. The final statement involves column P and column tilde Q. So for all practical purposes, I do not need column Q anymore, right? I can ignore it. I'm only going to look at the columns that I highlighted there in orange. So looking at those two columns, I'm going to create an AND statement. And when is an AND statement true? When they're both true. So on the first row, I have true and I have false, which gives me a false statement with AND in it. The second row, I have true and true, which gives me a true statement. The third row, I have false and false, which gives me a false statement. The fourth row, I have false and true, which gives me a false statement. And then we're done. All right. Little vocabulary. Logically equivalent. Logically equivalent are two statements that have the same truth value in every possible situation. And if two statements are logically equivalent, like P and Q, we write them with a triple equal sign between them. It's got 3 lines on it. Now, De Morgan's laws, they're actually on the screen, should have an extra line here. They should have 3 lines there. They're logically equivalent statements. So let's talk through De Morgan's laws and we will do an example. De Morgan's laws show that if I put a tilde on the outside of a parenthesed item, that there's a way to sort of distribute the tilde through and how it gets distributed. So the tilde, the negation of P and Q, is the negation of P, the negation of Q. Like, that's fine. But then the AND statement became an OR. Do you guys see that? It turned upside down. And the same thing happens if I start with an OR statement. An OR statement's negation becomes an AND statement. So it's almost like I'm negating all 3 pieces. I negate P, I negate and I negate Q. Okay? So we're negating all 3 components when we do De Morgan's law. Now, De Morgan's law's purpose is to create the negation of a compound statement. So this one first is just a symbolic, negation. It says P and tilde Q. So if I'm going to create the negation of P and tilde Q, what will I get? I'm going to negate each component. So what's the negation of P? Tilde P. What's the negation of the AND statement? OR. And what's the negation of the tilde Q? Q. And you're done. So you just negate all 3 pieces. So I want to show you that that actually gives you the right answer. Like, it's fine for us to say this works all the time, but it'd be nice to actually see that it really works. So we're going to do that with truth tables. So what we're going to do is we're going to create a big old giant truth table. The first columns are going to be P and Q. Right? And then the next thing we're going to do is we're going to actually take this statement and we're going to find the truth table for that statement exactly like it's written, okay? We're not going to try and distribute anything. We're just going to find it as written. So what does that mean? Well, take a look. Inside of the parenthesis, just like with algebra or whatever, order of operations, you work inside the parenthesis out, right? So inside the parenthesis, I have a P, and also inside the parenthesis, I have a tilde Q. I've got P in my table already, I don't have tilde Q. So the next column in my table is tilde Q. Now I have everything in the set of parentheses component-wise in there. I can now join them with an AND statement. So now I'm going to have P, and tilde Q. That takes care of everything inside the set of parentheses. So the last thing would be to do a column where I have the negation of that, the whole statement altogether. Tilde, that's not a good tilde. Let's try that again. Okay, so the negation statement all composed at the end. So far, so good? Okay, we're going to create this truth table and see what happens, and then I'm going to show you how we decide if it's logically equivalent to what we had before. So let's just stop there for a moment and create this truth table. So the truth table always starts out in column P with what? Yes, true, true, false, false. And column Q is always what? True, false, true, false. Now I need tilde Q, which I found before, which tilde Q is going to be what? False, true, false, true. Now I'm going to join with an AND statement, column P and column tilde Q with AND. We've already done this step, right? We did this a couple screens ago. So I have true, false, which gives me false. I have true, true, which gives me true. I have false, false, which gives me false. And I have false, true, which gives me false. So the last column is to simply take the column I just created and flip it. Do the opposite. Reverse it. Right. So false becomes true, true becomes false, false becomes true, false becomes true. And this would actually be done. So in some sense, my table's finished. That's the table for what we've already got. Now what I'm wanting to do is I'm wanting to compare that final column that I got to what happens if I do a truth table for this one right here. Okay? I'm just going to tack it on. I'm going to add it to the column I already have, the columns I already have, because I already have a P in my table. I've already got a Q in my table. What do I not have? I don't have the tilde P. And, oops, P. And I don't have what else? The or. I think that was the one you said, Jessica, right? Yeah. So I'm going to do a column for tilde P, and I'm going to do a column that puts all of it in there as tilde P or Q. So, tilde P, I got to go all the way back to the beginning. The P column was true, true, false, false. So what would tilde P be? False, false, true, true. And then I'll switch colors. We'll go to yellow. I'm going to compare the tilde. I've got to have a thicker highlighter. Where's my thicker one? Let's try that. There we go. The tilde P column, and I'm going to compare the tilde P column with the Q column. Okay, the ones that are now highlighted in yellow are the ones that I'm comparing. I need to take them and I need to join them with an OR statement. Now, we haven't done that. When is an OR statement true? When either one of them is true, or both, right? So on the first row, I have true and I have false, which gives me true. The second row, I have false and false, which gives me false. The third row is true and true, which gives me true. And the fourth row is false and true, which gives me true. And here's the name of the game. The name of the game is that this column right here and this column right here are our comparisons. And what do you notice? They're exactly the same. They have the same TF combinations in the exact same order. It's all identical. And according to what we wrote over here about logically equivalent is two statements that have the same truth value in every possible situation. That's exactly what happened when we created their truth tables. They have the same true, false in every scenario. So this right here shows that these statements, the original ones that I created with the tildes and so forth using De Morgan's laws, are in fact logically equivalent. All right, we're going to do one more with De Morgan's laws and we'll stop for today. We're going to use De Morgan's laws to write the negation of a statement as opposed to symbols. All right, the statement says, it is not sunny and I will go for a walk. There are three components that need to be negated. What's the first component? The first component is it is not sunny. When we negate it, we're going to do what you suggested. What's the second component? It's going to have to change. That's the third. I will go for a walk. And. So we've got three components. I've underlined them respectively. We're going to have to change all three of them to use De Morgan's laws correctly to change this to the negation of the statement. So what would it is not sunny change to? It is sunny. And take a look outside. Is it? It is. It's a nice sunny day out there. Well, it's a sunny day out there. And will become or. It's logical opposite there. How about I will go for a walk? I will not go for a walk. This is the logical opposite of it is not sunny and I will go for a walk. That last composite statement, that compound statement right there, that's me right now today. It's too cold out there. It is sunny or I will not go for a walk. But both statements actually could be put an and between there and it would still be true for me today. Any questions about De Morgan's laws and changing statements with them to their negations? Okay.